In this next lecture, we're going to be going into a little bit more depth on quantum circuits and quantum algorithms in the circuit model. Okay. So in a classical computer, well, a classical computer manipulates bits, as we all know, and abstractly bits are binary digits. And these are going to be physically realized in a two-level system. So that could be, for example, could be a light switch, could be a magnet, or in general, any physical process in which two physical states are distinguishable. So, for example, here's a physical process such that its voltage varies with time, and if there's enough of a distinction between the high and the low state, you can assign a 0 and a 1 to each of those states, and then you can take this evolution as encoding a binary string, for instance. Now, in classical computation, so this is still very abstract, but it's a little bit more concrete. We tend to not use Turing machines. I mean, although in principle, I suppose one could be physically built, but in practice, a much more useful model of computation is the circuit model of computation, which is from a complexity theoretic perspective, the circuit model is just as efficient as a Turing machine model, although so just as efficient in that large sense that we are interested in from complexity theory. So in the sense that a Turing machine would be actually very inefficient if you had one on your desk, but it's still efficient in the complexity theoretic sense, in the sense that you can efficiently simulate by using no more than a polynomial number of extra time steps in a Turing machine any computation that you can run in a circuit, and vice versa. So they're polynomially interconvertible in that way. And so for the rest of the lecture, we'll be talking about circuits, both in the classical context as well as in the quantum context that we'll get to a bit later. So in the circuit model of classical computation, we typically use, so actually we don't use this many, I'll get to that in a minute, but we use classical logic gates. So for instance, we have the AND gate, which is symbolized that. We have, do you still see my mouse pointer, by the way? Hello? Just,
it is the same
okay, yes, just want to make sure because I'm in full screen, and so I don't know, sometimes computers
same color of the screen, eh? It is almost the same color as the screen, but it is possible to see.
It is possible to see? Okay, good.
As long as it moves, it's okay. As long as it moves.
Right. I know it disappears after a while. Okay, so we have thank you. So we have the AND gate, we have an OR gate, and we have a NOT gate, and those are standard conventions for how they're depicted. Given these basic gates, we can construct a classical circuit, which we can build up to represent a more complex logical program. Right. So here's a very simple one. Here's an instantiation of a material conditional, right? So that we build up using the NOT gate and the OR gate. Now, in classical computation, we can talk about a universal. We can speak of a universal set of computational gates. So it so happens that this set of gates is universal in the sense that just as I did here, I can construct any other logic operation I want using just these two gates. Here's another universal set. So, and rather than OR, I can just limit myself to AND and NOT, and that will also allow me to perform any any classical any classical circuit I like. Okay, I can construct anything I like with just those two. Here's another universal set, and this one is called, so this gate is called the Nand Gate, and it implements not and. And I only need this single gate in order to construct any logic circuit I like. Should have given an example, but anyway, so I can use that and only that gate. And here's another universal set. This is the NOR gate, which instantiate the not, not A or B operation, and that's also a universal set. So using that single gate, I can construct any logic gate that I like, any logical circuit that I like. In quantum computing, rather than bits, we manipulate quantum bits. And another word for that is a qubit. I think David Merman doesn't like that. So I forget who came up with that name, but I remember David Merman didn't like that name. He tried to rename it with very little luck. But anyway, so qubit is a quantum bit. And abstractly, these are represented by vectors in C2. And they're physically realized by a two-level quantum system. For instance, the spin of an electron in a particular direction is a two-level. Can be thought of as a two-level system in that sense. So here's a visualization of the state space for a qubit. And this is also called the block sphere. So I didn't actually write it on the slide, but it's BLOCH, so block sphere. And the surface of the sphere is where the states of a qubit live, at least the pure states. We won't be talking about mixed states today. But for pure states, these are all going to live on the surface of the sphere. And the computational basis state, so I don't know if you can see it, but there's a little Z there, a little X there, and a little Y there. The computational basis states are the Z eigenstates, are the eigenstates of the Pauli Z operator, which are 0 and 1. Okay. And so these are the states that we typically initialize a computation, a quantum computer in, and typically it's going to be 0, just by convention. And the general form for a qubit state in the Z basis is given by a linear combination of 0 and 1. And with respect to an arbitrary basis, given the two elements of the orthonormal basis, it's going to be a linear combination of those two vectors, those two basis vectors. Okay, so now quantum. So that's the space of a qubit. Now a quantum logic gate. Okay. So it's analogous to a classical logic gate, but in quantum computing, we describe quantum logic gates by unitary transformations. And so remember that unitary transformations are reversible operations, and they're norm. So that's different from classical computing. And we saw a little bit of that yesterday, and Roberto and Midis' talk, how unitary transformations are reversible. And another aspect of unitary transformations is that they're norm preserving, which is good because we want it to be the case that after running a qubit through a quantum gate, it remains the state of a qubit. We don't want that not to be the case. Although we do have measurement gates, but we'll get to that later. So I'll go through a few examples of quantum logic gates. And one quantum logic gate is the X gate. Okay, and the X gate corresponds to the Pauli X operator. And so X applied to 0 gives you 1, and X applied to 1 and 1 gives you 0. So it's, as I said before, it's analogous to a kind of NOT gate. And in terms of the state space of a qubit, it implements, so here's the X-axis. So you can think of it as, kind of rotation around x, right? And it's a pi rotation around x. So it takes 0 down to 1 and 1 up to 0. Okay. There's also the y gate, which is a rotation around y. And this will take 0 to 1, but it'll introduce a phase factor of I. And it'll take 1 to 0, but it'll and thereby introducing a phase factor of minus I. Then there's the rotation around Z. And so this, it just rotates around Z. So not surprisingly, it'll take 0 to itself because it doesn't change the orientation of Z, right? And it'll take 1 to itself, but again, it'll introduce a phase factor of minus 1. Now, another important gate is what we call the phase gate. So in some books, you'll see this as S, actually. For various reasons, I want to call it R. So a phase gate is a pi over 2 rotation about Z. Okay. And so again, it'll leave Z as it'll leave the 0 unchanged, but it'll introduce a phase factor of I to 1. And finally, for now, it's the Hadamard Gate. So this one's a little bit more complicated, and you've seen this one already yesterday, I believe. So the Hadamard Gate, in terms of rotations, what it instantiates is a pi over 2 rotation about y, followed by a pi rotation about x. And the result of that is if you start in the state 0 and you run through a Hadamard Gate, you end up in this superposition of 0 and 1. And similarly, if you start in the state 1 through a Hadamard Gate, you end up in this superposition of 0 and 1. Right? And these are two different superpositions, obviously. Okay, so that's the Hadamard Gate. The next important gate is the controlled NOT gate, or it's also known as the controlled X gate, because remember, X is a kind of NOT operation. And so here, so this is the way we were, if you just bear with me for 1 second. I want to see if I can get my selection again. Does that work? No, not really. Okay, well, anyways. So anyway, so if you have, this is the way we indicate the controlled NOT gate. So the 1 here refers to the fact that the control qubit is in the first position. Okay, so that means X here is our control qubit. And so what this operation implements is, so it leaves the control qubit unchanged, and it performs exclusive OR operation, or you could also think of it as as a modulo 2 addition of Y and X. So for instance, if here's the control qubit, here's the target qubit. If I start off with 0, 0, then okay, 0 is unchanged, and 0 exclusive OR 0 is 0. Again, 0 is unchanged here. 1 exclusive OR 0 exclusive OR 1 is 1. Okay. And if you have 1, 0, then again, 1 exclusive OR 0 is 1, and 1 exclusive OR 1 is 0. So far, it might not be clear why I've called it a control gate. But the reason we call it a control gate is because in addition to thinking of it as an exclusive OR operation, we can also think of it this way. So depending on the state of the control qubit, we will either do something or not to the target qubit. So if the control qubit is in the state 0, then nothing happens, right? So if the control qubit is in the state 0, then whether it's 0 or whether the target qubit is 0 or 1, it doesn't matter. It'll stay at 0 and 1, 0 or 1. On the other hand, if the control qubit is 1, then we flip the target qubit, right? And so that's why we call it a control NOT gate. In terms, it's equivalent to this way of thinking about it. Now, I'm not going to be doing this, but it sometimes in some books, or maybe even in the same book, you might have it both ways. The control qubit might be on the right side, right? So it depends. That's why we have this notation here. Another important gate, although I won't be talking too much about the Toefl Gate today. It's not going to come up importantly for my purposes. But another gate is a Toefl Gate, and this is a 3-qubit gate. Okay, so and we visualize it as a so it's similar to a controlled NOT gate, which is a 2-qubit gate, but this one has 3 qubits, and it's called a controlled NOT. Okay, so basically, what happens is both of the control qubits have to be set to 1 for the exclusive OR operation to take place. Finally, we have a measurement gate. So a measurement gate is depicted by this meter, by a kind of meter here. Like often we'll actually put the basis that the measurement is in there, but for our purposes, we'll only be measuring in the computational basis. So Z is going to be implicit. So a measurement gate implements a projective measurement in a given basis. And as I said, typically it's going to be the computational basis. And it's going to implement a probabilistic transition. So whereas all of these other transitions are deterministic, and just like in the deterministic Turing machine, for instance, the measurement gate you can think of it as a kind of probabilistic transition in a similar sense to the way that a probabilistic computer will transition probabilistically. Okay? So in an abstract sense, you can think of it that way. It's just a probabilistic transition. And we can use measurement gate. They don't necessarily have to come at the end, but they usually do. But we can use measurement gates in the middle of a computation, and in those cases, they'll affect probabilistic transitions. And so, as we saw this morning, given a qubit that's in this superposition state, if you send it through this measurement gate, which we'll see with Z basis, then it's going to yield 0 with probability given by the mod square of alpha, and 1 with probability given by the mod square of beta. And here's an example of a circuit that we can build up to from these basic gates. This, I'm not going to be discussing this one in detail, but this, it just so happens, is the circuit for the teleportation algorithm. Okay. And so as you see here, the measurements are actually performed in the middle of the computation. These double wires, which again we're not going to be talking about today too much, these are supposed to be conducting classical information, whereas the single wires are conducting quantum information. So here we have qubits. So we have qubits. They go through a Hadamard gate. Then there's a measurement. Now it's effectively a bit, and then the bit goes here, and so on and so forth. So there's an example of a quantum circuit. This is a Bell state. Oops, sorry. Here's a Bell state, and so just as a shorthand, we say that so 1/2 of the Bell state goes on this wire, the other half of the Bell state goes on this wire, and so on. Okay, so let's go through just a few basic equivalences between gates. So if you chain 2 Hadamard gates together, that just gives you the identity gate, and that's not surprising because the Hadamard is a unitary gate, and so that's just the way unitary gates are. Another sometimes useful equivalence is this one. So if you take an X gate and you sandwich it between 2 Hadamard gates, that gives you effectively a Z gate. And the opposite is also true. If you take a Z gate and you sandwich it between 2 Hadamards, that will effectively give you an X gate. And so this one is also an equivalent, more of a definition than an more kind of definitionary equivalence, because a controlled NOT gate just is a controlled X gate, because X is a NOT gate, right? So it's just another way of writing it, you could say. Okay. So the gates, so as putting the Toefl Gate aside, the gates that I've introduced so far are the so-called Clifford group of quantum logic gates, and this is going to be important tomorrow when we discuss the particular result that has to do with Clifford gates. And so the X, Y, Z, the phase gate, and the Hadamard gate, and the controlled NOT gate. So these are all single qubit gates, plus you have this 2-qubit gate. These are all, they all form the Clifford group of gates. It's a particularly important group, but I won't get into exactly why it is right now. This is not a universal set of quantum gates. It's close though, because we just need to add one more gate, and we do get a universal set. And this is called the S gate. And in some books, this will be referred to as the T gate, actually, but for various reasons, I want to call it S. And so the S gate, again, it introduces a phase factor when applied to 1. And together, this is not the only universal set of quantum gates, but it's an important one. And together, these can be used to construct any quantum circuit. In the sense, as I think it was Roberto that mentioned yesterday, that in the sense that we can simulate any quantum operation to arbitrary accuracy. So it isn't like, go back to the classical case again. So it isn't like this, where it's not so much, well, it is a simulation of a logic operation or of some algorithm. But it's, simulation would be a kind of pedantic way of putting it, because it's an exact simulation, right? Like there's no, it's not, the idea of asymptotically approaching something isn't really at play here. This is an exact simulation of a logic gate, of a logical operation. Whereas in the quantum case, it isn't really true. What we have is an approximate, but an approximate in a particularly strong sense, and it asymptotically approaches. So we can approximate to arbitrary accuracy any quantum operation. And so the reason this is important is because in practice, it's extremely hard to build gates that take more than 2 qubits. So even the Toefl Gate would be extremely hard to implement in practice. And so we're typically limited to 1 and 2 qubit gates. And so we would, on the other hand, we would like to be able to, in some cases, simulate an operation that is performed on n qubits, that might be performed on n qubits. So some kind of unitary transformation that transforms some larger system of n qubits. And we need to be able to approximate that operation using 1 and 2 qubit gates. And this result, that these gates are a universal set, is extremely useful from that point of view, because it means that simulating an arbitrary transformation is within the realm of practical possibility, arguably. So that's why universal set is important, and that's what it manifests itself as when we come to, that's what the sense in which it simulates an arbitrary transformation comes down to. Okay. So those are some of the basic elements of a quantum circuit. And so in the quantum circuit model, we typically think of so in 2000, so there was some research in the 90s, a lot of research in the 90s coming up with different algorithms. And DiVincenzo in 2000 wanted to write down a set of criteria to determine when, we could say something is, like a functioning quantum computer. Like, how do we know when we have one? And he isolated 5 different criteria for for when that would be the case. And these apply to the circuit model of computation. As I'll get into briefly a little later, it's not the only model of computation, but with respect to the circuit model, this is typically what we would like to see in a quantum computer. So we would like it to robustly represent quantum information. So we want it to be able to manipulate qubits, essentially. And the other thing is, we'll see this a bit more tomorrow. I think, yeah, a little bit more tomorrow. We'll see that. So, what a quantum computation generally does, perhaps not in all cases, but it seems like possibly in all cases, it generally entangles its qubits, right? And so, when a system is coherent in that way, it tends to decohere when it's introduced to noise from its environment. And so we need to be able to shield the computer effectively enough so that decoherence effects are minimal in comparison to the running time of the computer. Okay? So essentially, we want to be able to shield the computer from noise, which is what decoherence amounts to. Okay, and the third thing we would like is if we have a quantum computer, if we want it to be a universal quantum computer, then it should implement the universal family of unitary transformations. Now, maybe we don't want it to be a universal computer. I mean, there are special purpose classical computers, and we still call them computers. And so maybe there will be a role for a special purpose quantum computer. In fact, maybe that's actually more likely to be the case in the future, is that we'll have not necessarily universal quantum computers, but quantum computers that implement particular types of transformations and that are useful for particular purposes. The fourth requirement that DiVincenzo, I think I misspelled it, DiVincenzo, I think. Anyway, it's one of those. I think it must be DiVincenzo. Anyway, so sorry about the typo, if that is a typo. So the fourth requirement is that we should, in this quantum computer, we should be able to prepare a fiducial initial state. So generally, the initial state is going to be such that all of the inputs to the system are going to be zero. Initialize in the computational basis state 0. Right? But I mean, that's just a convention. But the important point is that we should be able to, so whatever our convention is, the computer should be able to prepare the input to it in that way. And then finally, at the end of the computational process, we need to measure the output. And so these are the 5 criteria that DiVincenzo expressed for a quantum computer to be an actual reliable universal quantum computer. Okay. Let's talk a little bit about some algorithms in the quantum circuit model. So before I talk about particular algorithms, I want to talk a little bit about oracles. So an oracle is used in many quantum computational algorithms in the circuit model. And an oracle is a particular device that's used by, it's also used in computability theory, but in computational complexity theory, the way we imagine an oracle is as an imaginary, so it's also an imaginary black box in computability theory. But in computability theory, it's the number of time steps doesn't figure importantly. But in complexity theory, we imagine that this magic black box is such that it can determine whether some given string X is in a particular language L in one time step. So it's like the Oracle at Delphi, except that unlike the Oracle at Delphi that might take weeks to give us an answer, this will just give us an answer in one time step. And so we can imagine that we have an oracle to compute, for instance, the satisfiability problem, which is an NP-complete problem. Or we could even imagine that we have an oracle to compute the halting problem in one time step. We don't care about how it does it. We just imagine that we do. So why do we do this? Well, it's because it's conceptually very useful, because it allows us to talk about the complexity of an algorithm relative to that oracle. And why would we want to do that? Well, I mean, often so it's often useful to abstract away from the implementational details of something when you're constructing something, for instance, right? And so if you think that the implementational details of determining what a function yields on a given input is not that important, then we can just abstract away from those inner details and talk about the behavior of the algorithm abstracted away from the implementational details of that particular thing, right? So it's useful conceptually, and then you can compare different algorithms with respect to one another, relativized to an oracle. Now, as I said, many quantum algorithms are oracle algorithms, and there's nothing wrong with that in the sense that they're, like as I said, it's useful conceptually to speak in terms of oracles, but when we want to make claims about the non-relativized complexity theoretic propositions, so whether some algorithm A is more efficient in an absolute sense than some algorithm B, then oracles might give us evidence one way or another for that proposition, but they don't give us conclusive evidence. So like a really jarring illustration of how oracles can cease to be useful is the fact that there exist oracles relative to which P is equal to NP, and there exist other oracles relative to which P is not equal to NP. So oracle analysis doesn't seem useful for the purposes of actually answering this basic question of complexity theory. But nevertheless, one can talk about oracles and talk about how to apply and talk about algorithms relativized to oracles in very useful ways. But just one needs to take them with a grain of salt. And so in the context of quantum computing, so you've heard, I'm sure you've heard that there's no proof that quantum computers are more efficient than classical computers. And so what that means more specifically is that there's no non-relativized proof. But there is, so one can prove quantum speedup relative to certain oracles, and we'll see a couple of cases where that's true in a bit. Okay, so let's start off with Deutsch's problem. So everybody starts off with Deutsch's problem, but I guess you kind of have to because it clearly illustrates how things work. So Deutsch's problem was introduced by David Deutsch in 1989, and it's a nice way to illustrate one aspect of the way that quantum computers operate. And so the problem is this. So we imagine that we have a function that takes a function from 1 bit to 1 bit. So it goes from 0, 1 to 0, 1. And this function is going to be constant when the output is the same regardless of the input, right? So you can imagine, like the output is always 0 regardless of whether it's 0, 1 or always 1. A function is going to be balanced when its outputs are assigned in equal proportions to its inputs. So for instance, here's the identity function, okay? And so the identity function just doesn't change its input, but it's balanced, right? Because half of the outputs correspond to half of the inputs. And the same is true here, even though this is a very different function. This is a bit flip function, but it's still the case that the outputs divide the inputs evenly. And so that's a balanced function. And so now we can consider the question of if I give you some function and I ask you, tell me whether this function is constant or balanced. And so we can consider a classical algorithm that would invoke an oracle to answer that question. Now, the classical algorithm would need 2 invocations to get an answer deterministically, because if, for instance, I applied the function to 0, it will give me 0. If, for example, I applied the function to 0 and it gave me 0, then that bit of evidence is going to be consistent with either the identity or the bit flip hypothesis. In order to determine which hypothesis is the correct one, I need to run it again. So you need 2 invocations of the oracle in the classical case. Okay, so it doesn't mean that if you don't abstract from the oracle, maybe there's, I mean, probably not here, but maybe there's some structure to this function that would make you do it more efficiently, perhaps. Like I said, I don't think that would be the case here, but we are abstracting, we are relativizing to an oracle here. Okay, so we can't consider anything in a way. We're limited to this kind of flat-footed way of solving the problem classically. But be that as it may, that's the way the analysis is working. We're talking about an oracle. Now, quantum algorithm is going to need only one invocation of the analogous oracle in its case. Okay, so we'll see how that works. So I'm basing my presentation on this really nice textbook from written by David Mermin, 2007. So the way that the algorithm works is that we prepare 2 qubits in the state 0, either the initial states. Then we begin by sending the 2 qubits, each of them through an X gate. So start with 2 qubits here, then we apply an X gate to each of them, followed by a Hadamard gate applied to each of them. And so, well, so these are basically NOT gates applied to each of these. So what you get as a result is Hadamard operation applied to 1 and another Hadamard operation applied to 1, which is going to give you, if you work it out in the way that I showed you earlier, it's going to give you this expression. So we're going to have, so 1 transformed by the Hadamard gate goes to 1 over root 2, 0, 1, and similarly for the other one, and then that's just a combined expression. And we can rewrite that as this superposition. And now the next step, once we have this, is now we apply a unitary transformation. And so this is where the oracle comes in. Okay, so we apply a unitary transformation to the input. Well, it's 2 qubit to the input and to the first and second qubits, right? So we apply the unitary transformation to both of these. And the way this works is going to take, it's going to leave X unchanged, and it's going to take the exclusive OR of Y with the result of applying our function to X. Okay, so now if we apply the unitary transformation to that, what we get is this. Okay, so we get, so 0, 0 goes to 0, and then 0 exclusive OR f of 0, 1 0 exclusive OR f of 1. Okay, just in the way that that specifies. Okay, so now we have this expression, and now this is the state of our computer. Now it's going to be useful to define f hat of x, which will define to just be 1 exclusive OR f of x. Okay, so that's going to allow us to replace these guys here, and that'll yield this expression. Okay, so 0 f of 0 minus 1 f of 1 minus 0 f hat of 0 plus 1 f hat of 1. Okay, so these go here. Okay, so now this is the state of our quantum computer. Now imagine that f is a constant function. So that what that means is that f0 is equal to f1 and f hat of 0 is equal to f hat of 1. So that allows us to, so in that case, that would allow us to re-express the state of the computer in this way. Because these are the same now, so now we just have 0 minus 1 f0. And these are the same now, so we just have 0 minus 1 f hat 0. Okay. Why did I highlight? Oh, right. Okay. So now we can just manipulate that and put it in this form. Okay. So this is the state of the computer when f is constant. Oh, that's why I highlighted that, because that's extremely important. Okay. When f is balanced, now, so in the case where f is balanced, we have it that f0 is not equal to f1. However, f1 is equal to f hat 0, and f0 is equal to f hat 1. Okay. So what that means is that this state ends up being expressible in this way. Okay. And now we can re-express it like this. And simplify. And so now what we have is, so the second qubit is in the same state in either case, whether it's constant or balanced. But the first qubit, when f is constant, the first qubit is in this, this superposition state. And when f is balanced, it's in this superposition state. So we're almost done. So we can actually distinguish these two these two states with an x measurement. But imagine that we don't have x measurements available. And I mean, they're hard to implement, but computational basis measurements would be easier. So what we can do now is we can apply a Hadamard gate to the first qubit. So a Hadamard gate is going to transform these into these, right? And now we can measure the first qubit. And if it comes out 1, then the function is constant. And it comes out 0, then the function is balanced. And so there you go. So there were a lot of steps in that algorithm, right? But the important step is the number of calls. The important thing in this context is the number of calls to the oracle, right? So whereas in the classical case, we had 2, right? Called f0. We called f twice. In the quantum case, we only call it once. So that's how you can do that in one identification. Now let's move on to the to a slightly more complex example. Yeah, there's plenty of time. Okay, so this is another example of a deterministic algorithm, and this is a little bit more impressive, and it's a little bit more complicated as well. And so this is called the Bernstein-Vazirani problem, and I forget when this was first discovered. I guess it was in the 90s sometime. So this is the Bernstein-Vazirani problem, and the problem is this. So we imagine we have some number a, which is an integer. And we imagine that a is in between 0 and 2 to the n for some n. And that means that we can represent a as a binary number in this way, right? So a binary number, an n position binary number. So the nth minus 1, the nth minus 2, and the 0th position. So we can give a binary representation like that. And now imagine that we have this function that acts x, so that takes, so a is held constant. We imagine that a is held constant, and so f of x takes a bitwise modulo 2 inner product of a and x. And so it's an inner product, just like all the other inner products that you know and love, except that instead of addition, we use modulo 2 addition. Okay? Otherwise, also known as exclusive OR. And now the question we want to answer is, how many times do we need to invoke the function f in order to find out the value of a? So imagine, so I have some function. I have some a that I want to find, and I have a grab bag of strings x of length n. And how many of those do I need to grab out of the bag and apply f to in order to find out the value of a? That's the question. Now, classically, classically, you're going to end up needing n invocations. And let's take an example, n is equal to 5, just to illustrate. So when n is equal to 5, then your bit string is going to look like this, right? A0, A0, A4. And now suppose I want to find the 0th bit. Then what I can do is I can grab out of my grab bag of binary strings, I can grab an x that looks like that. And now to find the 0th bit, I can take f of x, which is a dot product that. And so these ones all evaluate to 0, whereas this one evaluates to a0, and that's our 0th position. And you can do the same thing for all of the different bits. Okay? And that's going to require n invocations of f, which is not bad actually, because like n is linear, right? And linear time is not a bad thing in computational complexity theory. But it's still n invocations of this oracle that we need to make. Okay, so let's look at the quantum algorithm for solving this problem. And this is the Bernstein-Vazirani algorithm. And again, I'll be basing a presentation loosely anyway on Mermin 2007. Okay, so now in the quantum algorithm, we begin with n plus 1 qubits, and n of them are initialized in the 0 state, and one of them is initialized in the 1 state. So, I mean, I guess in a way that contradicts what I said before, where we want to initialize everything to 0, and that's okay. If you really want to be, yes.
Michael,
yeah.
Sorry, a short question.
Yes.
By Patricia, is it simple to prove that there is no classical algorithm that is more efficient for Bernstein-Vazirani problem? Did you get my?
Yes, I got it. I mean, I haven't seen a general proof of it. But I'm guessing it's not too hard I'm guessing it's not too hard to prove that, but I haven't seen a general proof of it.
Okay.
Typically one isn't given. Typically they just present it in the way that I did and rely on the reader to be convinced. But I don't know if there's a general proof of it. It's such an artificial problem that yeah, such an artificial problem that I guess it doesn't attract the interest of enough classical theoreticians who want to solve it. It's useful for illustrative purposes. But one thing that would lead me to say that that this really is a lower bound is that again we're relativizing to an oracle. So it's not as if we can take advantage of some structure that's implicit in evaluating this function. So like that's typically what happens, right? So like when we want to make an algorithm more efficient, often what we'll do is we'll look into the structure of something that we thought was a black box, and we'll see that, oh, we can actually do this and we can do that, and we can trick our way out of it in that way. So here, by imposing the relativization to an oracle, we're explicitly excluding that. Right, so this is the only thing you can do is you can invoke an oracle, right? And so well, I haven't seen a proof, an explicit proof of it. I would say that, yeah, I would say that it's not a controversial proposition, but I could be wrong about that. Okay, so is that okay?
Patricia,
is there a follow-up or yeah?
Is it clear?
Oh, sure. Yeah, thanks.
Okay.
Yeah, so that's okay. Although I guess if what we're trying to say is that a quantum algorithm is better than a classical algorithm, it had better be better than any classical algorithm now.
Of course. Yeah.
So we better be able to prove, like, however artificial this problem is, which I understand, we absolutely need to show that this is the best we can do classically. Otherwise, whatever this square root improvement or whatever it is that we're going to get in quantum doesn't really mean a lot. And we've seen this thing, like the Google experiment has just been a paper in Archive of a few weeks ago saying, oh, we've done it in like however many minutes now, rather than any 100 years or whatever it was. So this is really crucial, no?
Yeah, absolutely. So I mean, all I can tell you is that no one knows of a better algorithm than this to do it classically.
Okay. Okay, cool.
Right.
Thanks.
Okay. So okay, so if I'll go on. So now let's look at how we run the Bernstein-Vazirani algorithm on a quantum computer. Okay, so again, we begin the quantum computer in the state. So we have n+1. So again, it's strictly speaking, it's not correct to start with 1, but we can imagine that we start with 0 and run this through an X gate. So just saves a bit of writing, because if we want to be very pedantic about it, we want to initialize all our qubits in the state 0. But now let's just imagine that we started with state 1 here. And so we send these n qubits through an n-fold Hadamard gate. And we send one qubit through this other qubit also through a Hadamard gate, but separate one. And so this gives us, essentially, if you take every qubit, take 0 to 0 plus 1 over root 2, 0 to 0 plus 1 over root 2, this big expression here. Well, this one goes to 0 minus 1 over root 2. And we can compactly express that in this way, right? So if you take this large multiplication, what you're going to get is 0, 0, 0, 0 plus 0, 0, 0, 0, 0, 0, 1 plus 0, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, and so on. You're going to get you're going to get the linear combination of all of the possible values of an n-bit string. Okay? That's what this is. Whereas the last qubit is going to be in this state here. Okay, so now we have this. And now the next step is we want to apply this unitary transformation, this large unitary transformation to these qubits. And now the unitary transformation is going to work as follows. We apply this. So here, when I have this xn here, just for clarification, what that means is that this state is a state of n qubits. Okay, that's what I mean there. Okay, so now we apply unitary transformation to this big tensor product state. And what that does is it leaves the xn unchanged, but it takes y and it takes the exclusive OR of y with the result of applying the function to x. Okay, now recall that f of x is going to be either 0 or 1. Okay, and this is because it's modular to addition, right? So it can only ever be 0. The answer can only ever be 0 or 1. Okay, so the answer is going to be in 0 or 1. So if f of x is equal to 1, then what that means is that we flip whatever y happens to be. And if f of x is equal to 0, then we do nothing to y. Now suppose that f of x is equal to 1. Then since y is equal to this, we have y is transformed into this, right? Okay, because again, we did flip. And which is just the same as just taking the same expression that we began with and introducing an overall phase vector of -1. Okay, so the bit flip corresponds to an overall change of sign. Here. So what that means is that we can re-express express this expression, okay, this part of it, as a change of sign depending on the value of f of x. Okay, so if f of x is equal to 0, then that just evaluates to 1, and we don't change the sign. The overall phase factor, if that evaluates to 1, then we do change the sign. So now we have this state for the quantum computer. Okay. the next step is to apply more Hadamard transformations, so more Hadamard gates. So we do the same thing that we did before, basically, right? So now we apply an n-fold Hadamard gate to these qubits and a Hadamard gate to that qubit. Now the action of a Hadamard gate on some arbitrary n-qubit state x. Okay, so let's first consider the case of one qubit. Okay, so if it's one qubit, it's going to be either 1 or 0. So if x is equal to 0, then remember that Hadamard gate takes 0 to 0 plus 1 over root 2. So minus 1 to the 0 is 1, so we get 0 plus 1 over root 2, while if x is 1, then we get 0 minus 1 over root 2. Okay, so that works out correctly, and we can even more compactly describe this as by saying, so where here y refers to these, right? So the sum from y is equal to 0, 1 of minus 1 times minus 1 xy. Wait a second. Right, no, that's right. Okay, minus 1 xy times y, 1 qubit. Okay, so for n qubits, we have this generalizes to this expression. Okay, so we can rewrite that, the state of the quantum computer in this way. Okay, so let's start from the beginning again. Okay, so now we have this initial state. We apply all these Hadamards to it. We apply unitary transformation, and we apply Hadamards to it again. Okay, so the first step we end up getting this state, so which is what we started. This is a superposition of all possible binary strings of length n. And then this is the last qubit. Now we can use the trick we just used before, and so we can when we apply the unitary transformation, this amounts to an overall introducing an overall phase factor here, and now we want to apply the Hadamard gates. Okay, and now the Hadamard gates allow us to re-express in the way that we showed before the combined state of the system in this way. Okay. Now remember that f of x is bitwise modulo to addition, right? And so given that, and in particular, it's bitwise modulo to addition of, it's the dot product of a and x. So given that, we can manipulate this expression, and that will give us this expression here. Now this whole expression, again, because it's a dot product of a and x, we can re-express this as the product, okay, of the components in this way. Okay, so now we have this big state. Now imagine that, so this is, okay, so this is so the yn here refers to these states. So this state, okay, the state of these qubits. Now imagine that the number y that's represented here is not equal to a. Okay. So again, recall the way this was defined. If y is not equal to a, right? So imagine we put in y for a here. So imagine instead of a we have y here. Then because it's not equal to a, and there's some j such that and there's some j such that aj plus yj is equal to 1, because one of them will be 0, because it'll differ in one position, right? The bit strings will differ in one position. So for one position, a bit of y will be 0, and a bit of a will be 1, or vice versa. If that's the case, then if we evaluate this here, then what we end up is then we end up getting 0 as the amplitude for that y, right? So all of the y's that are such that they are different from a will get amplitude 0 in this superposition. Whereas the y that is a is going to get an amplitude 1. And so the state ends up being this one here, essentially. And so basically, so the y just becomes this. And so basically, we can just now measure the n-qubit first register, and that will give us the value of a. Okay. So that's the way the Bernstein-Vazirani algorithm works. So it's, and again, essentially, so like, there's a lot of stuff happening here, right? So there's these giant Hadamard gates, and measurements and so on, and there's a lot of stuff happening here. But in terms of oracle calls, there's only one oracle call. Okay? One oracle call in the case of a quantum computation versus n oracle calls in the case of a classical computation. And while that might not sound that impressive given all of the overhead, if n is very large, it quickly gets to be more and more impressive. Okay? But again, still, even when n is very large, it's still the case that linear time is still efficient. It's still quite efficient, actually. But be that as it may, this is the case. Okay, so do we have time to go through the Deutsch-Joscha algorithm? Maybe quickly. Yeah, maybe just quickly. So the Deutsch-Joscha algorithm is another algorithm, and it's similar to the Bernstein-Vazirani and the original version of Deutsch's algorithm in the sense that they're deterministic algorithms. Deutsch-Joscha generalizes Deutsch's problem. So whereas in Deutsch's problem, what we want is we want to go from 0, 1 to 0, 1. In the Deutsch-Joscha problem, we imagine that we have that our domain is bit strings of length n. Okay, and we have a function that takes bit strings of length n to a single bit. And again, we ask the same question: is this function constant or balanced? And so here, so the way I don't have the fancy illustrations here, but we take the so this is actually H. Yeah, actually, I think this one was a little bit quick. But I mean, I wrote this slide up a little bit quick, but here there should be a tensor product Hn. Okay, so we take Hadamard gates over the whole thing. And again, this is going to give us a superposition of all possible values of x of length n. And this qubit is going to go to 0 minus 1 over root 2. Okay, and in the next step, what we do is we apply unitary transformation. So this unitary transformation is going to take y and take the exclusive OR of the result of applying f to x. Okay, so now if we take the unitary transformation on this big state, what that gives us is that gives us this again. So this is going to, in a similar way that we saw with the Hadamard gate, this is going to introduce an overall phase factor here, which it allows the solution to be a little simplified. So what we end up getting is, so I won't go through the basic. So you're applying this unitary transformation to the whole thing. So you would think that the last qubit gets changed, but what happens is just the way that it happened before. Applying this transformation to y basically introduces a phase factor to this qubit that's based on the value of x, value of f of x, and now we can move this phase factor away from here and put it here. So that's essentially what's happening here. But it's the same thing that was going on in the previous algorithm. Okay, so now we have this state of the computer, and we imagine that f is a constant function. Now imagine that f is constant, and imagine that it's equal to 0. So now, if f is constant and is equal to 0, then so if a constant n is equal to 0, then the phase factor goes away. Well, I mean, it just goes to 1. Okay, and so we have that. And now we apply Hadamard. Again, there should be a tensor here. So it should be hn times h. And so we apply Hadamard's again, similar to the we did in the last algorithm. And now this is going to go, and it's clear because you're applying. So we started from here. We applied the Hadamard Gate, and we got this. And now we apply Hadamard Gate again, and we get back, right? So it didn't exactly work that way, but you can see why this will bring you to 0n. Okay, and this is just 1, right? Because like when you taking a Hadamard Gate on 1 gives you this, and taking a Hadamard Gate again gives you 1 again. Okay, so this is the state you end up with if f is constant and equal to 0. Now imagine that f is constant and equal to 1. Okay, so now this is unfortunately written. There should be a times in here, but essentially this phase factor stays, right? And now what you have is negative 0n1. And so either way, in the case where it's balanced, or it's constant, sorry, either way, measuring the input qubits, like the n input qubits, will give you 0 with certainty, because the overall phase factor is not going to matter for the purposes of our measurement. What about the case where, oops, slide, but what about the case where f is balanced? I hope you can all see that. So in the case where f is balanced, then half of these terms in the summation, in this summation, are going to have positive phase, and half of the terms in the summation are going to have negative phase. And so when you add them all up, it's going to give you an amplitude of 0. And so when you measure these qubits, then the n first qubits, what you're going to get is something other than 0 with certainty. So if you get 0, then it's constant, and if you get something other than 0, then it's balanced. And that's it. So again, you have, I didn't have the diagram, but it's the same idea. Again, you have one invocation of the oracle that allows you to determine the answer to this question with certainty. In the classical case, and I don't have the proof on hand, but I remember working through this once. Maybe I should have reviewed that, but I remember working through this once, and it's certainly the case that a deterministic classical algorithm is limited to 2n/2 + 1 oracle invocations, whereas a quantum algorithm, as we just saw, is limited to 1 invocation. Okay, so that's a generalized Deutsch-Jewish algorithm. As we saw for the Bernstein-Vazirani, we have a deterministic classical algorithm. So anyway, so the Deutsch-Jewish algorithm, this is an exponential speedup because this is an exponential number of steps. So this is the most impressive of the ones that we've looked at, right, in that sense. So a quantum algorithm requires 1 and only 1 invocation, whereas a deterministic classical algorithm requires many, many more. Now, Simon's algorithm, which I'm not going to go through, is a probabilistic algorithm. So what it does is, so what Simon's algorithm does, the steps are not that different from what we've seen, but now instead of giving us a state that we can measure and distinguish and use to distinguish one answer from another with certainty, what we have is a state such that we can measure it and give us with high probability the answer to our question. And if the probability is not high enough, we can always run the algorithm again and make the probability higher. So Simon's algorithm determines the period of a periodic function that's periodic under bitwise mod 2 addition. Okay? And the number of oracle invocations grows only linearly with n, whereas for the classical algorithm, classical probabilistic algorithm, It's going to grow exponentially with that. Shor's algorithm builds a bit off Simon's algorithm, but so it's an algorithm for factoring, but what it really does is it converts an algorithm for period finding into an algorithm for factoring. But instead of being periodic under modulo 2 addition, the functions that are considered are functions that are periodic under ordinary addition. And so one thing of note about Shor's algorithm, which is another reason why it's so interesting, is that it's not relativized to an oracle, right? So this represents an improvement in an absolute sense over the best classical algorithm. So one reason for not presenting it here is because the actual quantum part of Shor's algorithm is not so interesting. I mean, it's important, obviously, but it's not the most interesting part of that algorithm. Like much of the legwork has to be done classically. But Shor's factoring algorithm runs in time that's polynomial in log n, right? Whereas the best classical algorithm is exponential in log n. So it's an exponential speedup, even though the best classical algorithm has a sub-exponential running time, but it's an exponential speedup, relative speedup, relative to the best classical algorithm known. Now, what's interesting about Shor's algorithm is that, so about factoring in particular is that, so factoring, while the quantum algorithm is provably better than the best classical algorithm, it's not the case that it would be wildly implausible that we could figure out that we could come up with a classical algorithm to do better. Okay, so if the time was truly exponential, if it was just 2 to the n, then it would be implausible that we could. It might be more implausible that we could do better. But given that we've already discovered some structure to this problem that allows us to reduce it in this way, it's not implausible. I mean, I think it's more implausible than plausible, but it's not completely implausible that we could discover further structure that would allow us to decrease this complexity even more. Because again, it's all about finding structure that we weren't aware of originally, and that's typically how you improve an algorithm. So Grover's algorithm, which I'll mention last, is what's not interesting about it is that the speed up is only modest. So rather than exponential like it is for Shor's or for Simon's, the speed up is only quadratic. But what is interesting about it is that it's actually a speed up that's with respect to an NP-complete problem. And unfortunately for the quantum computer, it's a provably optimal speedup. You can prove that you can't get better than that. Okay, so let me finish up with just a few words about the question of what explains quantum speedup. Okay, so I only want to talk a little briefly about this. I want to survey some of the answers that have been given. So one thing you'll have noticed, so we didn't see exactly this, but we saw essentially something like this, right? So we begin with a computer that's in something like a state x0, and then we transform it into a state where we have x again and f of x. So it seems like we have f is being evaluated for all of the possible values of x simultaneously. And so this is the thesis that this is actually what's happening, what is happening in the computer. That this is literally the case is called the quantum parallelism thesis. And one defender of this thesis is Armand Duhl. So he defends it. There's a further thesis, which is called the many worlds explanation of quantum computation. And this starts from the quantum parallelism thesis, but then it further posits that corresponding to each of these parallel computations is a different world within which these parallel computations are taking place. Okay? And so one nice defense of the many worlds explanation, I think, is that by Hewitt Horseman from 2009. And there have been some potential problems identified with the many worlds explanation. So I've criticized it in a 2012 paper, and Scott Aronson has also written about it more briefly in a paper from 2013. And so two potential problems is two potential problems that you have for the explanation. So that doesn't necessarily mean insurmountable problems, but these are problems that anyone who's defending this view will have to come to grips with. Is on the one hand, we have the lack of decoherence in a quantum computation, right? I mean, of course, there is decoherence in the sense that we can't perfectly shield a computer from the environment. But by lack of decoherence, what I mean is that generally, quantum computation is going to entangle its qubits. And in order for the computation to work properly, then those qubits need to remain coherent for the length of the computation. But typically, in discussions of many worlds, at least it depends on what kind of Everettian you are, I guess. But if you're an Oxford Everettian, like David Wallace, for instance, then you have to either say that. So if you're an Oxford Everettian, like David Wallace, then you want to use decoherence as a way of distinguishing worlds from one another, right? You want to say that worlds that don't cohere with one another can be considered as distinct ontological worlds. So in the context of quantum computation, although visually it gives you the appearance of many computational worlds, nevertheless, this is an entangled superposition that we're looking at. And so you either have to use another criterion for world identification in the context of a quantum computation, or you have to argue that the old decoherence criterion still applies in some way. And so, but it's a challenge. It's a challenge that one has to answer if one wants to defend that view, I think. Another potential criticism is that the many worlds explanation, and what I say here applies equally well to the quantum parallelism thesis. So Dual doesn't defend the many worlds, but he defends the quantum parallelism thesis. But what I say applies to both, I think. Well, the first one applies to the many worlds in particular, but the second one would apply to both. So the second one is that the parallelism that you see here is clearly visible in the circuit model, but when you simulate a quantum circuit algorithm in a different model, the parallelism might not be so evident. And so that's another challenge for someone who wants to defend either many worlds or the weaker quantum parallelism thesis, to explain how you have parallelism even in those other models where it doesn't appear as easily. Another candidate for an explanation of quantum speedup is entanglement, in the sense that, as we saw in the first lecture earlier, the state space for a combined quantum system is given by the tensor product of the individual vector spaces, whereas for a classical system, the combined state space is given by the Cartesian product. And so we'll see this in a little bit more detail tomorrow, but what that means is that the state space for a combined quantum system is going to be exponentially larger than the state space for a combined classical system. So you can think of the idea as like there's so many more possibilities in the quantum state space that you can take shortcuts in your computation. And so maybe one way of visualizing it. And so this has been defended by a number of people. There's a problem for this view, is that there's something called the Gauss-Mill theorem, and I'm going to be talking about this in detail tomorrow. So the Gauss-Mill theorem shows essentially that there are quantum algorithms that involve entanglement that are efficiently simulable by a classical computer. And so if you want to say that entanglement is the reason for quantum computers being able to be faster than classical computers, then you need to explain why sometimes they aren't enough to do it. Right? And so I'll be talking about that in more detail tomorrow. And then there are other explanations for quantum speedup. So Jeffrey Boob has what he calls a quantum logical explanation. I won't go into that in too much detail now. there are others. So I mean, similar, like the people. So there are people defend contextuality as the explanation for quantum speedup, and so on and so forth. Different features of quantum mechanics that people would say are the reason for why quantum computers are faster than classical computers. And the jury's still out as to which is the right explanation for it. And the jury's still out even with respect to the fact that quantum computers actually do have a quantum speedup for classical computers. So I mean, these explanations will go by the board if quantum computers actually aren't faster. What we can say though is that you can distinguish between two ways you can compare quantum and classical computers, right? So if you think of, I want to factor two numbers, right? For example, or I want to solve some abstract function. Then I can talk about how to solve that using a classical computer, and it can be vastly different from the way that I solve it using a quantum computer. So the oracle obscures that, but actually, like the way that we solve a problem can be vastly different in one model of computation than another, even if they're similarly organized in circuits. Right? So that analogy can be a little bit misleading. But you can also ask the question, so imagine I have a quantum system evolving in a particular way, and given that I want to simulate the evolution of that quantum system, you simply can't do that. If you want to simulate all of the steps in the evolution of that system, it's simply going to be more efficient to do it in a quantum way. Irrespective of the more abstract problem of finding an answer to a particular question. Now, important considerations for answering these questions some of them are the following. So on the one hand, like how do we measure complexity, right? So are oracle invocations good enough for those purposes? So I've argued that those are useful. They're not necessarily going to give us the answer to the question of why quantum computing is faster than classical computer. Another question is what actually counts as a computational step? Can we count computational steps in the same way in quantum computing as we do in classical computing? So as long as we can count them in the same way, it doesn't matter what they are. But arguably, maybe it's a bit more. The question is a bit more interesting to that. Maybe we do need to think about that question a bit more carefully. Another consideration. Something that I mentioned. Do oracles hide structure that would allow a classical computer to solve a problem efficiently? So in the case of Shor, that's not applicable, but in the case of the other algorithms, it certainly is applicable. While in the case of Shor's, we know that there is structure to the problem, right? And so that we've already taken advantage of to get a better classical algorithm. Could be that there's more structure, right? Another consideration is that we need to compare apples to apples and oranges to oranges, right? So the generalized Deutsch algorithm, right? A deterministic classical algorithm requires this many oracle invocations, whereas a quantum algorithm only requires one. But you can do a lot better if you have a probabilistic classical algorithm, right? With respect to the oracle, that's important because there's a subtlety that I'll mention tomorrow. But there's with respect to the oracle, you can do a lot better with the classical probabilistic algorithm than you can with the quantum algorithm. Than you can with the classical deterministic algorithm, which makes the comparison, which makes how impressive the quantum algorithm is less so. Right? And so, probabilistic and deterministic computation have different criteria for success. Right? So even probability 1 in probabilistic computation isn't necessarily going to be good enough in a deterministic algorithm because you always have your epsilon. And then there's overhead issues, right? And then these are more technical issues, there's a whole field of error correction which I haven't talked about, and how complicated is it to have a computation that that is robust in the sense that is able to correct errors that arise during the operation. Issues related to state preparation. I mean, arguably these are going to be minor when we have, you know, a large number of qubits, but of course they're important when we have a small number of qubits, as we do now in current instantiations of quantum computers. Okay, and finally, we talked about the circuit model, but there are other models of quantum computation, just like there are many models of classical computers, right? So we have a circuit model of classical computation, we have a Turing model of classical computation, we have von Neumann architectures, and so on and so forth. In quantum computing, we also have many different models. We have measurement-based quantum computation, adiabatic quantum computation, topological quantum field theory model of computation, and so on. And just as in the classical case, where all of the different models of computation have been proved to be efficiently simulable by one another, and again, we'll talk about that more tomorrow, it's also the case that so far, all of the different models of quantum computation that have been discovered have been proved to be equivalent to one another.